Hello everybody, thank you Jay for the nice introduction. I'm going to present you a joint work with Fedor, Ryabinin and Alexey Gotsman from IMDEA software, and I myself from Télécom, SudParis and INRIA. So the context of this work is geo-replicated data. Data is now available from multiple locations where it is used by different clients. Those locations are kept in sync by using a replication protocol. Those protocols ensure that replication is transparent and efficient. They also ensure that, despite failures of one or more locations, the system is still available, data is still available. So the gold standard to ensure this kind of properties is to use state machine replication. State machine replication uses a log at each of the replica, and commands that are accessing the data are executed in the log order. To ensure that, state machine replication is executing a consensus instance. This instance is deciding the position of the next entry in the log. So for instance, in the example on the slide, we have three replicas, R1, R2, and 3, and three commands ABC. The order in which they are going to be executed is B, then A, then C. And replica 1 has already executed B and A, and it is about to execute C. This approach is implemented in many distributed systems, such as Zookeeper, Spanner, and Apache Cassandra. In SwiftPaxos, we are taking a different road. We are ordering only the commands that are conflicting. Conflicting commands are commands that are accessing the same variable at the level of the application. So let us consider that ABC are accessing different variables that are defined at the bottom of the slide. Command A is accessing variable X, setting it to the value 42. Command B is accessing Y, changing its value to 7, and C is storing the sum of X and Y in variable Z. To ensure that conflicting commands are executed in the same order, SwiftPaxos is computing for each command the set of dependencies. That is the command that will execute before it. And it is executing the command with respect to these dependencies. So going back to the example, A and B are accessing different variables, so they can execute in any order. And there is no arrows, no dependencies between them. Actually, in the example, replica 2 has already executed A, whereas replica 3 has executed B. In the case of command C, there is a dependency with B and A, in the sense that B and A must, the two of them execute before command C. Command C is depending on both A and B. There are three invariants in SwiftPaxos to ensure liveness and safety. The first invariant says that at each of the replica, the dependencies are acyclic. This ensures liveness, that every command executed by a client eventually returns. The second property says that replicas agree on the dependencies. That is, for each command, they compute the same dependencies. The last property says that commands that are conflicting, that in accessing the same variables, see each other. In more formal terms, it states that if X and Y are conflicting, either X is in the dependencies of Y, or the converse is true, that is, Y is in the dependency of X. This last property ensures that the system is linearizable. SwiftPaxos is a new, strongly consistent replication protocol. It maintains at least the speed of Paxos. It executes commands in optimal time. In a single round trip, if there is no contention, that is, commands which are conflicting or received in the same order at the replicas, and if this is not the case, it takes 1.5 round trip to execute a command. The key novelty of SwiftPaxos is its ability to do a double vote. That is, during agreement, a replica can vote twice. It can vote for its own proposal and vote again for the proposal of the leader. Let's see in detail how the protocol is working. For this, we consider a system with 5 replicas, R1 to R5. R5 is submitting a command, command B, to the system, and this command is being received by R3. R3 answers with its proposal as dependencies for B, and it proposed that B is ordered first. If a quorum of replicas is reached and send back the same dependencies spontaneously, then the command can execute. So here, command B is executing right away in the fast pass, because all the replicas in the quorum formed by R3, R4, and R5 are spontaneously proposing that it executes first. In this case, for a client executing at replica R5, it takes 2 message delays to execute the command. This is optimal. Let us consider now a more involved example in which we have 2 commands A and B. These commands are received at R3 in the order command B, then command A. R3 is sending back to R1 the fact that B should be ordered before A. If the commands are accessing different variables, that is, they are commuting, there is no need to order them. In such case, R3 is simply saying that there is nothing that precedes A despite B was received, because there is no need for creating a dependency. So once again, if a quorum is reached, the command can execute in the fast pass. So the protocol is able to leverage the commutativity at the level of the application. Dependencies allow also to execute command when there is no contention, that is, commands that are conflicting or received in the same order at the replicas. So let us consider a third command, C, that is doubling the value stored in variable x. This command is received in the same order at the replicas R1 to R3. That is, A was received first, then C. So they are spontaneously proposing that the system keep this order. And again, the command can execute through the fast pass in a single round trip. So with SwiftPaxos has this specific feature to use the spontaneous order of the network. As I said, another property of SwiftPaxos is that it allows to do double voting. So let us consider another example to illustrate this thing. We have 2 commands, B and D. B is assigning 7 to variable y, and D is returning the sum of x and y. We have also a leader replica, which is replica 4, which will solve a disagreement between the replica if it happens. So let us consider that replica 3 is receiving first command D, then command B. If the replica 4 has received B first, there is a disagreement between the replicas regarding the ordering of B. To correct that, SwiftPaxos is allowing the leader replica to broadcast its proposal, and replicas that are receiving a proposal that is not the one they sent correct their vote. They vote a second time to correct their proposal. So in that case, R3 will vote to order B first. So this is possible because at a given ballot, the leader of the ballot is a member of all of the quorums of that ballot. If such an assumption holds, then it is possible to do such a vote correction, a double voting mechanism. So this ensures that in the worst case, we have 3 message delays, that is Paxos speed, to execute a command. A last feature of SwiftPaxos is to permit non-collocated clients, that is, clients that are not collocated with a replica, to receive a quick response to their operation. So in a common case, the client is sending to a quorum of replica its command, and then the command has to be executed at one of the replica before it receives a result. So here, for instance, command is executed at replica 5, which returns 0 as the result of the sum of x and y. SwiftPaxos has an optimistic execution mechanism to accelerate this, the execution of command. It executes the command at the leader replica. So here, replica 3 will send back 0 as the result of the execution of command D to the client. And if this result is sent together with the dependencies, and the dependencies of a quorum match the one of the leader, the client knows that it is a durable result, the final result of the execution of the command. And so a last characteristic of our protocol is that it can quickly reply to non-collocated client. So let's see now in practice how it performs in comparison to existing solutions. So we have compared in AWS, SwiftPaxos, again, 7 other competitors. There are 13 AWS sites. 5 of them are replica sites and 10 are client sites. We are using an OP service and commands are carrying a 1 kilobyte payload. We are comparing on the left, when we are changing the conflict rate, the latency of the protocol with respect to Paxos. And on the right, we are plotting the cumulative distributed function of the latency across all of the sites when we have a fixed 2% conflict rate, which is a value that is commonly encountered in practice. So Paxos is the baseline, that is, this is the 1x speedup. We have first competitor is N2Paxos. So N2Paxos is a variation of Paxos in which the 2B messages are sent to all of the replicas as a commit message, and it provides, in the experiment we have done, around 5% latency improvement over Paxos. Egalitarian Paxos and generalized Paxos are 2 protocols that are originating commutativity at the application level. However, as seen in this slide, their performance is quickly dropping with the conflict rate. The higher the conflict rate, the slower those protocols are. The best competitor is CURP, which was published as NSDI in 2019. It is around 18% faster than Paxos on average. And SwiftPaxos is up to 40% faster than Paxos. And as seen on the right with the CDF, it's always at the speed of Paxos. That is, there is no Paxos point on the left of the CDF of SwiftPaxos. We have also evaluated our protocol in 2 applications. The first application is an application in which we're pipelining commands. That is, clients are sending command without waiting for their result. This is a pattern we can see, for instance, when changing a version of an object, and before switching its pointer, we pipeline the changes to create the new version. So in this experiment, we are comparing SwiftPaxos, ePaxos, and CURP, and we are changing the size of the window from 1 to 10,000. And we can see that in this evaluation, SwiftPaxos is up to 49% more faster than CURP. This comes from the fact that this protocol is not able to leverage the spontaneous ordering of the network. We have also run YCSB, which is a key value store benchmark, and we have compared SwiftPaxos again against CURP and ePaxos. And also in the paper, we are proposing a variation of SwiftPaxos in which we can execute reads at any of the replica, and those reads are linearizable. And we can see in the plots that SwiftPaxos, as well as this variation, are faster than those 2 protocols that are CURP and egalitarian Paxos. So to conclude, SwiftPaxos is a new leader-driven state machine application protocol that can execute commands in optimal time in a single round trip when there is no contention. that is, commands that are conflicting or ordered by the network, and in 1.5 round trip otherwise. So in practice, it achieves between 16 and 29% better latency than Paxos, and its throughput is up to 3 times higher than alternatives. The protocol is particularly interesting with respect to metadata usage. In particular, when there are conflicts, there is no ballot change, something that you can see in fast Paxos or generated Paxos. The ballot is always kept the same as long as the leader is responsive. If you want to try the protocol, you can have a look on our GitHub repository and send us any question if you want. Thank you very much for your attention.